Next unit is on bonding, chemical bonding. And so we'll start with an overview of chemical bonds, what they are, why they form, and then we'll get into some examples of each. So there are actually three major types of chemical bonds. I know your notes only have space for two. They are known as ionic bonds. We have covalent bonds, and then there are metallic bonds. So ionic and covalent bonds occur between atoms in a compound, whereas metallic bonds occur between atoms in a metal. So the first two are the most common types that we'll talk about mostly in this unit. So why do chemical bonds form? Why is it that we can find gold, for example, in pure form in nature? Whereas sodium, for example, we can't find in pure form, we only find it in compounds in nature. Has to do with the stability of the atoms. And so gold atoms are relatively stable, therefore they don't need to form compounds. Conversely, sodium atoms individually are relatively unstable, and they can achieve stability by forming chemical bonds with other atoms to form compounds. So that is the very, very, very important key topic there. Bonds form to lower the potential energy of the bonded atoms, and in doing so, this makes them more stable. So some things that we're going to also learn in this unit, we're going to show through the use of orbital diagrams how molecules form. Visit Lewis structures. So before we drew Lewis structures for atoms and monatomic ions, this unit will learn how to draw Lewis structures for molecules and polyatomic ions. Basically anything that has covalent bonds, we can draw a Lewis structure for. With these Lewis structures, we'll use them to predict many things, one of them being molecular geometry, or the geometric shape or three-dimensional shape that a molecule or polyatomic ion takes. Letter F, something known as hybridization, so how an atom can form multiple bonds with other atoms in a molecule or polyatomic ion. We'll talk about polarity in bonds, whether a bond, covalent bond, is polar or nonpolar. We'll also look at polarity in molecules. So molecules as a whole can be classified as either polar or nonpolar. And then based on the polarity of a molecule, we'll be able to determine the type of intermolecular forces that occur between atoms, or actually between molecules rather. So let's look more in depth at ionic bonds and ionic bonding. Ionic bonds usually occur between a metal and a nonmetal. Technically, an ionic bond occurs between an atom that has a low electronegativity. So think about where on the periodic table are the elements with low electronegativities. That's primarily on the left side of the periodic table where the metals are. Bonded to an atom with a high electronegativity. So again, think about where on the periodic table the elements that have high electronegativities are located. These are on primarily the right side of the periodic table. So we can generalize and say ionic bonds occur between metals and nonmetals. Technically, the type of bond that occurs between atoms depends on the difference in electronegativity. So if there's a large difference in electronegativity, such as the case when you have a metal bonded to a nonmetal, the bond is primarily ionic. So this ionic bond forms, when it forms, it involves the transfer of electrons. So electrons are being transferred from one atom to another, and I'll show you how this occurs in just a little bit. A little review on atomic size, atomic radius. Atoms that gain electrons become larger, so anions are larger than the neutral atoms they form from. And then atoms that lose electrons become smaller, so cations are smaller than the atoms from which they form. So a couple examples here. Sodium, the neutral atom, versus the sodium ion. So Na plus is much smaller than Na. And then if we look at Cl versus Cl minus, the chloride ion is much larger than the chlorine atom. So this transfer of electrons that occurs when an ionic bond forms results in the formation of something called a crystal lattice. So we can see here Anytime we think about an ionic compound, and we've talked about this before, think about this. So we have these smaller sodium ions shown in whatever color that is, pink, red, we'll go with red, I guess, reddish orange. And then the chloride ions, larger chloride ions are shown in green. And you have a whole bunch of sodium ions and a whole bunch of chloride ions all stuck together. What's holding those ions together is something called an ionic bond. So now on the left, this ball and stick model is really not accurate. On the right, the space filling model is a little bit more accurate. It shows closely packed sodium ions and chloride ions. Let's do this. Let's show with Lewis structures how an ionic bond forms between two atoms. And we'll look at this same example. So let's do this. Draw the Lewis structure for a sodium atom right next to the Lewis structure of a chlorine atom. So we've done this before, so just put them next to each other. I want to show you what happens. Go ahead and pause the video and draw those now. Has one valence electron, so we have one dot around the symbol. Chlorine has 7 valence electrons, so I've shown 7 dots, different colors just because I want to show you what's going on here. So again, what happens is we have a transfer of electrons, but why does this transfer of electrons occur? Well, chlorine is much more electronegative than sodium. So the example, the analogy I like to use to demonstrate what happens with chemical bonding is tug of war. So let's say you have a tug of war, and on one side you have a group of 8-year-olds, and on the other side you have a group of 18-year-olds. So a group of high school students and a group of elementary school students. So the chlorine representing the high school students, the stronger team, sodium, the elementary students, the weaker team. The stronger team is so much stronger than the other team that it actually physically rips the rope out of the hands of the weaker team if we're talking about a tug of war. Well, same thing happens here. Sodium and chlorine are going to play tug of war with these two electrons here. Chlorine, being much stronger than sodium, actually rips the electron off of the sodium. And when this happens, when the chlorine rips the electron off of the sodium, you have the simultaneous formation of two oppositely charged particles. So let's draw now the Lewis structures of the ions that result. Now again, I just want to show you just with these different colors, difference in electrons. So chlorine had its 7 valence electrons. It gains one more electron from the sodium to complete its octet. You'll hear me say that term later on as well. And so look at what we have here. We have two oppositely charged particles. Remember that oppositely charged particles attract. So this attraction between the oppositely charged particles, sodium ions and chloride ions in this case, is called an ionic bond. Transfer of electrons resulting in the simultaneous formation of cations and anions. Let's do this. Let's try another example. Again, I want you to show with Lewis structures how the ionic bond forms between magnesium and fluorine. So we'll do the same thing. We'll take the Lewis structure for magnesium and put it right next to fluorine. And again, remember, keep in mind that atoms form chemical bonds in order to become more stable. So both of these atoms, in the case of sodium and chlorine, were able to achieve stability. Sodium in the way of losing an electron became stable. Chlorine became stable by gaining an electron. Bottom line, both atoms are stable. We need to show that here with the magnesium and fluorine atoms as well. So go ahead and pause the video, draw with Lewis structures, or show with Lewis structures, how ionic bonds form between magnesium and fluoride ions. So perhaps you ended up with something like this, which is not entirely correct. So though the fluoride here is stable, this magnesium is not stable. How does magnesium become stable? It needs to lose not one electron, but 2 electrons. So how are we going to show this? There's only one magnesium and one fluorine. Well, think about this. Think about what would happen if you took a piece of magnesium metal and put it in a container of fluorine gas. Well, a chemical reaction would occur, and during that chemical reaction, electrons would be transferred from the magnesium to the fluorine. Well, we don't have just one magnesium atom and one fluorine atom. We have a whole bunch of magnesiums and a whole bunch of fluorines. So let's do this. Let's draw another fluorine and let's see what happens. Well, one fluorine takes one of the valence electrons from the magnesium, and the other fluorine takes the other valence electron from magnesium. So I'm going to redraw how I showed it on the right side. So what do you notice? It takes two fluoride ions for every one magnesium for everything to be stable. So we have two fluorine atoms each gaining one electron from the one magnesium atom that loses two electrons. Look at the ratio of magnesiums to fluorides. This is why the formula for magnesium fluoride is written as MgF2. We have a ratio of two fluorides to every one magnesium. In the case of sodium chloride, both can achieve stability if we have just a 1-to-1 ratio of sodium ions to chloride ions. So again, just showing through Lewis structures how ionic bonds form between technically ions, how those ions form first of all. So we've heard this before, many but not all atoms tend to ionize so that they have the same number of electrons as a noble gas. So what's so special about a noble gas? Well, all the noble gases are stable. They're chemically inert, meaning they don't really like to be involved in chemical reactions. They don't need to form compounds to be stable. They already have a stable arrangement of electrons. Anything that does not have a stable arrangement of electrons can achieve stability by either gaining or losing electrons, or even sometimes, as we'll see in a little bit, sharing electrons. Seen this before as well. Sometimes we have monatomic ions. We also have polyatomic ions. Polyatomic ions, if you recall, are groups of usually non-metal atoms that act as a single ion. Make sure you memorize all the polyatomic ions that you were given in the past. Let me give those to you again based, we'll put them in order of charge. They are, once again, go ahead and pause the video so you can write those down one more time. All right, moving on to covalent bonding, sometimes called molecular bonding. So for covalent bonds, they usually occur between two or more non-metal atoms. As I mentioned before, the type of bond that occurs between atoms, it has to do primarily with difference in the electronegativities of the bonded atoms. So in the case of an ionic bond, you have one atom that has a high electronegativity, you have another atom that has a low electronegativity. However, in the case of covalent bonding, the bond usually occurs between two atoms that have fairly high electronegativities, where both atoms want electrons. Remember, electronegativity is the tendency of an atom when it is bonded to another atom to attract electrons or to pull electrons towards its own nucleus. So here we have two atoms that really both have a high ability of attracting electrons. And so the difference in electronegatividity of those bonded atoms is pretty small. So if the difference in the electronegativities is small, then the bond between the atoms is likely to be covalent. Here's a key part for covalent bonding. Since one atom is not strong enough to rip the electrons off of another atom, the two atoms that are covalently bonded will share one or more pairs of electrons. So a shared pair of electrons is known as a covalent bond. So sometimes atoms share one pair of electrons. Sometimes, as we'll see later, that atoms can share two pairs of electrons. And even sometimes atoms can share three pairs of electrons. So why does this happen? So remember, the bond forms in order to lower the potential energy of the bonding atoms, and this in turn makes them more stable. So here it is again, occurs when two atoms have roughly the same electronegativity. They don't have to be exactly the same, but when both atoms have relatively high electronegativities, The bond between them is covalent. Let's do this. Before we get to the orbital diagrams for molecules, let's show, like we did with the formation of ionic bonds, let's show as Lewis structures how covalent bonds form. So the first example we'll do is a bond between two, we can do two fluorines. Let's do something different because we'll do fluorines in our next example. Let's take two chlorines. So draw the Lewis structure for two chlorine atoms right next to each other. Go ahead and pause the video now and do that. All right, so here's what we have. Oops, I'm going to show this a little different this time just so we can see what's going on here. All right, so each chlorine atom has 7 valence electrons. In order to become stable, each chlorine wants to gain one more electron. So what happens? So this chlorine here on the right grabs on to that electron and pulls it towards its own nucleus. The chlorine on the left grabs onto this electron and pulls it towards its own nucleus. And so what ends up happening? And I'm going to show this. Let's do this. Let's show this again so we can see what's going on here. We'll show these with a different color. So one chlorine, the chlorines are not strong enough to rip the electrons off of the other. So instead of a situation where you have a transfer of electrons, these two chlorine atoms will just share this pair of electrons. So those two dots there between the two atoms represent the pair of electrons that the two chlorine atoms share. A shared pair of electrons is called a covalent bond. So let's do the same thing, this time with orbital diagrams, showing how a covalent bond forms between two atoms. Let's go back to our example of, well, not go back, but let's use fluorine as our example. So what I want you to do is to draw the orbital diagrams for two fluorine atoms, one here and then the other right below it. Orbital diagrams, that's lines and arrows. Go ahead and pause the video and I'll show you how the covalent bond forms between those two atoms. So here we have it. We have two orbital diagrams for fluorines, both showing that the fluorine atoms have 7 valence electrons. So what happens when two fluorine atoms form a covalent bond with one another? Well, again, a covalent bond involves a shared pair of electrons. I didn't mention this before, but two atoms can share a pair of electrons if their orbitals that contain a half, let me back up, when they have half-filled orbitals of one atom that overlaps with the half-filled orbital of another atom. So let me clean that up again one more time. Covalent bonds are results of the overlapping of half-filled orbitals. And so we see each fluorine has one half-filled orbital. And so what I'm going to do is I'm just going to box those two orbitals. And those two orbitals are the orbitals that overlap. The two fluorines then will share this pair of electrons. That shared pair of electrons we call a covalent bond. Let's try a little different one. Let's do this time, let's show with orbital diagrams how the bonds form, how a covalent bond forms between two oxygen atoms. So just like we did here, go ahead and draw orbital diagrams for two oxygen atoms right on top of each other, one above the other. And then see if you can predict how the bonds form in two oxygen atoms. Go ahead and pause the video. So we see that each oxygen atom has 6 valence electrons. Each oxygen atom, in order to become stable, needs to gain 2 more electrons. So how does this happen? Well, in this situation, the oxygens will share 2 pairs of electrons. Now, I don't want to put a box around all 4 of these electrons because that's going to show one bond where atoms are, I don't know, this looks kind of weird. So what I'm going to do is I'm going to box each pair of electrons that is involved in the formation of the covalent bond. So 2 electrons to make one bond, 2 more electrons to make the second bond. This is known as a double covalent bond. Now, before we move on to one more example, let me show you with Lewis structures, how this occurs. So again, the oxygens are going to grab onto each other's electrons. See if I can show this in a somewhat logical way. And so this time, what's going to happen here? Let's draw these electrons that end up being shared in different colors. And so what ends up happening is we get this. Where the two oxygen atoms share two pairs of electrons. Again, this is called a double covalent bond. All right, let's do one more example. Show with Show with orbital diagrams how the covalent bonds form in water. So I would start by drawing the orbital diagram for oxygen, and then see where you should put the orbital diagrams for the hydrogens in order to show how the covalent bonds form between the hydrogens and the oxygens. Go ahead and pause the video and do that now. Again, we see oxygen with its 6 valence electrons needs to gain 2 more electrons to become stable. Hydrogen has 1 valence electron. It wants to gain 1 more to be like helium, 1 more electron to become stable. And so we have one covalent bond that occurs between hydrogen and oxygen using those electrons, and another covalent bond between hydrogen, the other hydrogen, and again, oxygen's other unpaired valence electron. So there you have it. Transfer of electrons occurs for ionic bonds. Sharing of pairs of electrons occurs for covalent bonds. Next time, we will talk about how to draw Lewis structures for molecules and polyatomic ions. Thanks for watching.